In Part 3 of Lecture 5, we discuss priority and round-robin scheduling. Priority scheduling is based on the idea that some processes should start closer to the front of the line than others. Where a process enters the line depends on its initial priority, with processes of equal priority being scheduled on a first-come, first-served basis. If you are wondering if this is similar in some way to shortest job first scheduling, you happen to be correct. The shortest job first scheduling is a special case of priority scheduling, where the priority is based on how short the next expected CPU burst is supposed to be. Does a higher number indicate a higher priority or a lower priority? It depends on the operating system. Unix assumes that the higher the number, the lower the priority. IBM's MVS makes the opposite assumption. In either case, we assume that priority numbers are positive integers for simplicity's sake. How do we set priorities? Unix uses the time spent in the CPU, the time spent waiting on the ready queue, and user set factors as a basis for determining priority. All of these are internal factors. Other internal factors might be the number of open files, memory requirements for the process, I/O burst to the CPU burst ratio, and so on. The I/O burst to CPU burst ratio is an important factor because I/O bound jobs need quick access to the CPU but won't be there very long. Moving these to the front of the line generally increases throughput. External factors, though, may be equally important to the people running the system. Policy factors, such as process importance, types of funds and how much is available, the department that owns the process, and so on, may be just as important in setting priority. Starvation, as we already learned, is the situation where a process can sit almost forever waiting for the CPU, with no guarantee that it will actually get its use. For something such as shortest job first scheduling or priority scheduling, this is a very real issue, because a process can wait forever if higher priority processes keep entering the system before it gets to the CPU. On a busy system, a low priority job can wait for extremely long periods of time. If you have ever waited at a stop sign to cross a busy 4 or 6 lane avenue, you know how that would feel. There's a rumor that when they shut down MIT's IBM 7094 in 1973, they found a low priority job from 1967 that had not yet been run. The best way to get around the problem is to age the process, increasing its priority as it spends more time waiting for the CPU. Unix uses this to ensure that processes don't wait indefinitely, no matter what their original priority was. Let's look at this hypothetical situation where there are 5 processes with the burst times and priorities shown. Process 1 requires a 10 millisecond burst. Process 5 requires 5 milliseconds, with the others all being much shorter. They also vary in priority, with process 2 having a priority of 1, which in this case is the highest, and process 4 having a priority of 4, which in this case is the lowest. Here you see the results. Process 2 comes first, followed by process 5. Process 1 comes before process 3 because it has waited much longer. Scheduled in this fashion, their average processing time, including the wait, is 8 milliseconds, which is not too bad considering process 1's burst time. Round-robin scheduling is sort of similar to first come, first served, but with a twist that is especially suited for interactive systems. The most significant difference is that it preempts processes after their time quantum, their maximum time allotment, is over. Processes can always use less if they terminate or get blocked for I/O, but they cannot use more than a time quantum without going back onto the ready queue and waiting to get back into the CPU. The length of a time quantum varies from system to system, with typical values being between 10 and 100 milliseconds. The ready queue is usually implemented in a first in, first out manner, but that doesn't have to be the case. Unix uses round-robin scheduling and a priority queuing system, where the priority depends on the amount of CPU time used by the process, how long it has waited online, whether it had been blocked for I/O recently, and so on. Again, a process can always give up the CPU before its time quantum is over, but once it's over, it's back to the back of the line. Let's consider our three processes again with a maximum time quantum of 4 milliseconds. You'll notice that process 1 gets into the CPU first, but then gets bumped out pretty quickly. Processes 2 and 3 get in to do their thing, and then they're out. Process 1 comes back in and gets quantum after quantum because nobody else is waiting. The end result is a processing time almost as good as shortest job first. A round-robin algorithm can work well if the time quantum is the right size. If it's too large, it degenerates into a first-come, first-serve algorithm, and we can end up having the same kind of throughput problems that we saw in our scenario earlier, where a time-consuming CPU burst is ahead of two shorter ones. If the burst is too small, it can give the theoretical appearance of giving each user his or her own processor. But the problem is that the operating system's overhead begins to eat away at our available CPU time. It may seem like every job has its own processor, but that processor came out of the original PC with a 4 megahertz clock. Round-robin scheduling works reasonably well as long as the time quantum is long relative to the time it takes to switch from one process to another, the context switch time. The illustration that you see on the slide shows how many context switches there are for 3 different time quanta for a given period of time. If a context switch took a full millisecond, it wouldn't pay to switch in the last case. Fully half the time would go to switching processes. But if it took only a tenth of a millisecond, then it would be worth the effort.